Okay, and for the last bit of our first day of graphing polynomials, we're going to look at the effect degree has on real zeros and relative extrema, also known as turning points. So first of all, relative extrema, what do we mean by that? Something that's relative is how it relates to things close to it. And extrema means extremes, like the highest values and the lowest values. Okay, so for instance, this point here is a high point compared to all the points around it, but it isn't the highest point on the graph. Well, it looks higher than this high point, but look, the graph goes off to infinity. This is a local extreme value compared to the x values around it. This point here is the highest one, even though it's not the highest on the graph. So this is a relative extrema. It's a turning point. The graph reaches a maximum and then turns around. But it's not the maximum of the whole graph. It's just what we call a local maximum. Same, this one's more obvious. You see the graph comes down, it turns and goes back up again. This is a local minimum, but it's obviously not the lowest point on the whole graph. This is lower, and look over here. It's going off down to negative infinity. So we can use this information that's on this slide two ways. We can either be given a function, the equation of a function, and use this here to work out how many relative extrema or real zeros there could be on the graph. Or we can go the other way. From the graph, we can actually try and build an equation from what we see. So first of all, let's make sure that you actually know what a polynomial is. A polynomial is any function where you've got a list of terms. I've got written them out as really ugly terms, and I'm deliberately not holding it still because I don't want you to write this out. I mean, it looks horrendous. You don't need to understand it that way. Okay, but there's a list of terms. There's a list of things being added together. You have a polynomial if all these terms have got positive whole numbered powers of x, and the degree of the polynomial is the largest power you see. So for instance, this could be a1 is just a coefficient. It could be 3. This could be 3 times x to the 11, where this n is 11. Then maybe you've got 77 times x to the 10, one less than that number, minus 52 times x to the 9, or maybe there's none of these, and you go straight from x to the 10 to x to the 1. There might be some of these coefficients might be 0. Okay, so don't worry too much about how ugly this looks. Just know that the degree of your polynomial is the highest power of x you can see, and we call that n, the degree of the polynomial. Now, if you have a polynomial of degree n, it can have at most one less than the degree number of turning points. So for instance, if you had x squared, what does a graph of x squared look like? Wherever you draw it, parabola, it's got one turning point. Okay, does it have to have one turning point? Kind of, it does actually. It does, because it's got to go up and up at each end. But what about x cubed? X cubed could have at most 2 turning points, but you know what? It can have no turning points. There's x cubed. It's not got a relative extrema at all. But if you try and do all sorts of rubbish with it, if you had a complicated, that could be x cubed, where it could have 2 turning points. Okay? So it could have at most, whatever this number is, this graph here could have at most 10 turning points. Oh, let's have a go at that. That'd be horrendous. Let's try. Okay, at most. If it's degree 11, it's got to be an odd. It's an odd function, and it's positive at the beginning, so it's going to be ending up here and starting down here. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. Ooh, have I miscounted? How many turning points have I got here? Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, it could have up to 10, but it could simply go like this. Yeah? Do all turning points end up giving you a point on the x-axis? No. There's this, when you're turning around like this without going past the x-axis, this is implying this polynomial has actually got complex zeros, complex roots. So that's what this next line here is about. Real zeros. Real zeros turn into, they give you x-intercepts. If a graph, if a polynomial doesn't have any real roots, then it has no real zeros. Think, you learned this in Algebra 1. Remember, some polynomials do that, where the vertex is moved up. This has got no x-intercepts. This one would have complex roots. And do you remember you did something with b squared minus 4ac? The discriminant helped you work out if it had x-intercepts or not. So real zeros become x-intercepts, and a polynomial of degree n, this one has 11, can have at most 11 real zeros. Now, this silly example I drew up here had how many real zeros? 1, 2, 3, 4, 5, and 6. There would have been one there, and there would have been one there. 7. So it doesn't say it's got 11 real zeros. It says it can have at most 11 real zeros. So that's going from the equation to the graph. You use these rules. If you're going back from the graph to the equation, you do the opposite of everything. You say, instead of saying at most, you say at least, and this would be n plus 1, would be the relative extrema. That would give you, you add 1 to the number of relative extrema to get the value of n. Okay, and this would say at least. If it's got 3 real zeros, then its degree must be at least 3, but it could be higher. Okay, so let's have a look at this example here. That might not have been so clear how I put that. Okay, going from the graph to the equation. First of all, if we looked at this graph down here, it doesn't fit this at all. It's something totally different. However, what we can tell is because the end behavior is down on one side and up on the other, we can tell that this one is odd. So it could be 11, it could be 30, maybe it's 3. Let's work it out. All we know at this point, looking at those n's, because they go in opposite directions, we know it's to an odd power. We know n is an odd number, and because it finishes high, we know its leading coefficient is positive. So let's count the real zeros. Remember, the real zeros are your x-intercepts. So this one's got 1, 2, 3. It's got 3 real zeros. Now, this tells us that the graph must be at least, n must be at least, not at most, must be at least 3. The lowest number it can be is 3, because we're going backwards from the graph up to the equation. So we do the opposite of this, what's written here. The turning points, let's count them. Local maximum, local minimum. This is another local maximum. This is a local minimum. Okay, these aren't turning points. These are zeros. It's got 1, 2, 3, 4 turning points. So it can't be that. I can tell that straight away. Okay, it's got 4 turning points. So this number, the degree, must be at least 1 bigger than that. Because whatever n was, we'd take 1 off it to give us the most number of turning points they could be, at most. So this is telling me, if I'm going backwards, add 1 to this, and it's telling me the lowest value that n can be. This is telling me this n must be 5 or higher, this number plus 1. You're going in the opposite direction from the graph to an equation, so you're kind of doing the opposite of this. So you've got some of these to practice on your homework. There's only 1 slide for this. I hope it made some sense to you. The best thing is just try actually working with some and see where you get to. Okay, off we go.